Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about averaging, which is perhaps the most commonly applied operation when we perform data analysis. The goal is to give you a high-level overview of the topics related to averaging, so we're not going to be providing specific proofs and not a lot of examples, but you can find those in the specific videos on each of the topics. Let's get to it. We're going to talk about averaging. And the reason is that when we do data analysis, we average all over the place. Sometimes we average to describe a quantity. Sometimes we average to describe how a quantity varies. Sometimes we want to estimate a variable from another variable, and we can also use averaging for that. And finally, when we estimate causal effects from data, we often average. This is the plan for this overview video. We will start discussing what is the average of a random variable. Then we will talk about the variance, which captures variations in random variables, in random quantities. Then we will talk about the conditional mean and how it connects to the regression problem. And finally, we will talk about estimating causal effects from data, which is the causal inference problem. Let's begin by talking about the average of a random variable. So in this example, we have data that can be either equal to 3 or 4, and we're going to interpret it as samples from a certain random variable A. Now we would like to define a notion of average that applies to the random variable A instead of specifically to the samples. In order to do that, let's assume that we have many samples from this random variable. The average is obtained by just summing all the samples and dividing by the number of data, the number of samples. This, in fact, is equal to each of the values, the possible values of the random variable, in this case 3 or 4, multiplied by the number of data that are equal to those specific values, and then divided by the total number of data. Okay, hopefully you see that these two sums are exactly the same. But when we write things like this, we suddenly realize that the average can be written as multiplying each of the possible values by the fraction of times they're seen in the data. And this is just the probability that we see those values, which is captured or intuitively when we have a lot of data is equal to the probability mass function of the random variable at that value. So we obtain a formula for the average of a random variable where we sum over its possible values weighted by the corresponding probabilities. And this is how we define the average or mean of a discrete random variable. It's defined so that in a way it represents what we would get if we compute the average of many samples from the random variable. Let's take a look at an example. Here we have the PMF, the probability that a random variable is equal to different values. These values are goals. This is a little bit painful for me because I've just watched Spain lose to Morocco. I mean, good for Morocco, I'm happy for them, but I'm pretty emotional about our national team. So we have this, I have to pull it together and go on. So we have this PMF that represents the goals scored in a certain game. What if we want to compute the mean, which represents the average of many samples from this random variable? Well, we take each of the possible values, in this case from -2 to 3, and we multiply by the corresponding probabilities, and we add up all together. In this case, the average number of goals, the average goal difference, is going to be 0.2. What if we're interested in averaging a function of a random variable, where we can repeat exactly the same argument as before? Now we have this data, and maybe we're interested in the square, in averaging the square of this data. So basically, we apply the square to each data point, we sum them all up. Now, if we interpret this data as samples from a random variable that can have 3 or 4 as its possible values, this sum is essentially just 3 squared times the number of times that we see a 3 divided by the total number of data, which again is approximately the probability of seeing a 3 if, in the limit where we have many data. And the same for 4. Okay, this is the probability of seeing a 4, and we multiply by 4 squared. So this suggests generalizing our definition of the mean of a random variable to the mean of a function of a random variable, where We take the function, we sum over all the possible values, and we weight by the PMF of the random variable. This is useful because it avoids having to actually compute the PMF of this new random variable that is the square of the quantity that we're interested in. For a general function h, this is how we define the mean of the function of a random variable as the sum of all the possible values of the function applied to the possible values of the random variable multiplied by the PMF at those values. Remember, the PMF is the probability mass function that gives us the probability that the random variable is equal to each of those values. Notice that every time I'm going to write the definition of the mean of a certain quantity, I'm always going to put here the sum converges, and later on I will write if the integral converges. Sometimes these sums and integrals do not converge, and in that case the random variable might have infinite mean, or it might not have a well-defined mean. Later in the course we will talk about those issues. All right, so what if we have this function that maps goal difference to points? So in most soccer leagues, if you lose, you get 0 points. If you tie, you get 1 point. If you win, you get 3 points. So we have a function from the goal difference to the points gained from that game. We might not want to derive the PMF of this new random variable obtained by applying this function to the goal difference, this random variable I mean. But with our formula, we can compute its mean directly. Okay, what do? We just sum the possible values of g, we apply the function to them, and then we weight them by, so first we apply the function, and then we sum them weighted by the corresponding probability of g. So here we get that the average number of points is going to be 1.5. Again, I'm going a little bit quickly through the examples. You know, we have done them more slowly and more carefully in the specific videos dedicated to each of the topics. Now, what if we have two random quantities? Our data are like this. We have pairs of two quantities that we're interested in, and we want to compute the average of a function of those two quantities. For example, we want to multiply them together, okay, and then compute the average. Well, what is this equal to in terms of the possible values of the two random variables? In this case, one of the random variables can be equal to 3 or 4, and the other random variable can be equal to 1 or 2, okay, just for simplicity so that I can write things down easily. So here you can see that essentially we have all the possible values of the first one times all the possible values of the second one multiplied by the number of times that we see those specific pairs. So we can approximate this average when we get many samples as by multiplying all the possible values of this function that takes in the first variable and the second variable, multiplied by the corresponding probability of seeing that specific pair. What is this? That's just the probability, that's just the joint probability mass function of the two random variables at, in this case, 3, 1. Okay, hopefully that makes sense. This is because of the intuitive definition of probability as the fraction of times we see an event when we repeat the experiment that we're modeling with the probability over and over. So we end up with this formula where we sum over all the possible values of the two variables, and we take the function that we're interested in and we multiply it by the probability that we see those two specific values, and then we sum over all the possible pairs of values. We can do this for any function of two discrete random variables. We take all the possible values of the two variables, we plug them into the function, and then we sum over all those possible values, but weighted by the joint PMF of the two random variables. It's very important to use the joint PMF. This can be generalized to more than two random variables. If we have the entries of a random vector and we have a function of those entries, we can compute the average of that function, which we call the mean of the function of the random vector, by summing over all the possible values of the entries, and we're going to multiply again by the joint PMF. If we have a continuous random variable as opposed to a discrete random variable, a similar argument to the one that we use for the discrete random variable, but which involves limits, because now we have a continuous quantity, and it also involves integrals instead of sums, precisely because the quantities continuous will tell us, and this argument you can find in the specific video on the mean of a random variable, that we can approximate the average of many samples from this continuous random variable as a weighted integral where we're integrating over all the possible values that the variable can take, and now we're weighting it by the density of the random variable, the probability density function, the PDF. Of course, this only works out if the integral converges, otherwise the random variable will not have a mean, or its mean might be infinity. Let's take a look at an example. Imagine that you have a uniform random variable in the interval AB. How do you compute the mean of this random variable? You integrate all the possible values of the random variable times its density. What is its density equal to? 1 over b minus a, because that's the length of the interval. And that gives you that the mean is the midpoint of the interval, which is not necessarily the case for other random variables, but it is for a uniform random variable. If we have a function of a continuous random variable, perhaps not surprisingly, we take all the possible values of the variable, we plug them into the function, and then we integrate weighted by the density. And here you will not be surprised at all. If we have several random variables, what are we going to do? And we have a function of those random variables. We take the function and we integrate it against the joint density of the random variables of interest. What if we have a random vector? Same thing. All the possible values. So notice that this integral is over the d entries of the continuous random vector. We have to weight by the joint probability density function of the d entries and integrate over all of those. What do we integrate? The function that we're interested in, evaluated at those values. And I'm almost done. I know that this is a little bit repetitive, but I wanted to remind you of all the ways in which we compute means. Notice that all of these ways actually represent the same thing, which is an average of many samples of this quantity that we're interested in. Sometimes we might want to compute a function of a continuous and a discrete random variable. In that case, we take the function of interest and we weight it by either the marginal PDF of the continuous random variable times the conditional PMF of the discrete random variables, or vice versa. This is exactly equivalent because of the chain rule for continuous and discrete random variables, which can be applied in the two different orders. And the reason why we have to do this is that there's no joint PMF for a continuous and discrete random variable, and no joint PDF for a discrete and continuous random variable, so we have to use the marginals and the conditionals. Let's take a look at a quick example. Imagine that we're flipping a coin and we apply this Bayesian idea that the parameter of the coin is a random variable itself, and we say that it's a random variable that is uniform in 0, 1. If we want to compute the mean of the coin flip, this mean of the coin flip is a function of a continuous random variable, and I haven't said it here, but the coin flip, we're going to represent it by, let me pick, by a random variable a, okay? So we have the mean of a function of a and theta. This is a very simple function, it's just a. What are we going to do? We take the function and we multiply it again by the marginal and the condition, the marginal of one of them, the PDF in this case, because that's what we know of the continuous random variable, and the conditional of the discrete random variable given the continuous random variable. We sum over all the possible values of the discrete random variable, we integrate over all the possible values of the continuous random variable, and we get the mean. This is, so remember that the PDF is 1, and this is the conditional PMF of the discrete random variable given the continuous random variable. We don't need to sum because the value for 0 is going to be 0 because a at 0 is 0. Okay, so again, I'm going a little bit quickly through the examples, but I don't want this video to last for 2 hours. So the mean at the end of the day is 1/2. Okay, so now we have defined the mean of a random quantity. Now we go full circle and we ask, okay, but what if we have some data? How do we estimate the mean of the random variable that is being modeled, that we're using to model this data? We have come full circle because, of course, what are we going to do? We're just going to average. This should be no surprise because we have defined the mean of a random variable precisely so that it represents this average. All right, so we call this the sample mean, but it's funny that we do it this way, right? As if the mean of a random variable is some kind of fundamental concept and then we're trying to approximate it, whereas in reality it's kind of the opposite. We defined the mean so that it represents what would happen when we average many samples from the random quantity, but it is what it is. So we call this thing the sample mean. What is the sample mean? It's just the arithmetic average of whatever data we have available. And of course, we divide by the number of data. All right, so this is the same for discrete and continuous variables, and this should not be surprising because for both types of variables, this is how we actually define the mean, so that it represents this average. Let's take a look at a specific situation where we would apply the mean to do some data analysis. We have hourly temperatures at 134 weather stations in the US. We're not going to start looking at 134 histograms. We would go crazy. But if we just represent each of the temperatures by the mean temperature over a year, we can have a really quick idea of how the temperatures are in the US. So here you have the mean temperatures, where the radius of these circles is proportional to the mean temperature. We immediately see that it's much hotter in the south than in the north. Okay, so the mean gives you like a quick description of a random quantity. Let's take a look at the mean of parametric distributions. Okay, so we're going to start with a Bernoulli that has a certain parameter theta. Before we look at the mean, when you see averaging, you might remember that in maximum likelihood estimation, we averaged a lot. So we derived the maximum likelihood estimator for the parameter of a Bernoulli. What was it equal to? You just average the data. It was equal to the sample mean. This is a little bit surprising at first, but then when you actually compute the mean of this random variable as a function of the parameter, you realize that the mean is exactly equal to the parameter. So when we're estimating the parameter, it makes a lot of sense to just plug in the sample mean. This coincides with the maximum likelihood estimator, but this general idea of just seeing how the parameter is related to the mean and sometimes also the variance and other moments of the distribution, and then plugging in the estimate for those moments is called the method of moments. What happens for the geometric distribution with parameter alpha? The maximum likelihood estimator that we derived was just 1 over the sample mean. And surprisingly, the mean is actually equal to 1 over the parameter. So again, this method of moments estimator is exactly the same as the maximum likelihood estimator. We didn't need maximum likelihood. We could have just said, oh, look, the mean of the distribution is 1 over alpha. Let's just estimate alpha as 1 over the sample mean. We will see that this is going to happen for the rest of the distributions. So for Poisson, the estimate is the sample mean, and the mean of a Poisson is indeed equal to its parameter. For an exponential, the estimate was 1 over the sample mean, and the mean of an exponential is 1 over the parameter. And for the Gaussian, the estimate for the mu parameter, for the mean parameter of the Gaussian, is equal again to the sample mean, and the mean parameter of the Gaussian, which is great given that we called it the mean parameter, is actually equal to the mean of the distribution if we compute the corresponding integral. All right, so now we're going to see that the mean is great, but it can be severely distorted if there are extreme values in our dataset. So here we have a dataset of salaries in the NBA. You have both a histogram and a rock plot that tells you the salaries of individual players. So here probably we have LeBron James, Kevin Durant, and people like this. You see that most players earn very little, comparatively to the other players. And some of them earn a lot of money. The mean of this data set is $5.86 million. Now we can ask how many players earn more than the mean, and that's less than 1/3. So the mean is not that representative. It's not a typical value as we would generally expect from an average. So what is going on? In order to understand what is going on, let's take a look at a simple example where we have a distribution that is constant here that has constant density between minus 4.5 and 4.5, and the same density, but at a really large value around a large constant x between x minus 0.5 and x plus 0.5. So if we look at samples from this distribution, we're going to get most of the samples here, but from time to time, we're going to get a really large sample close to x. If we compute the mean of this random variable, it's dominated by x. It's equal to x over 10. So if x becomes really, really, really large, the mean is going to be dominated by this 10% of values, and it's not going to really represent the value of the typical values that we see there close to 0. In contrast, if we use the median is equal to 0.5 no matter where this guy goes, because we always have 50% of the probability here. Okay, no matter how large x becomes. So in situations where we have extreme values that distort the mean, the median is a very useful substitute. In the case of the MBA salaries, it's probably better to represent a typical salary as a median salary, which is $2.39 million, as opposed to the mean, which is $5.86 million. So more than double. The mean of a random variable has two very important properties. The mean of a linear combination of random variables is equal to the linear combination of the means of those random variables. This is called linearity of expectation. We use it all over the place, and it always holds. It's also true that the mean of the product of random variables is equal to the product of the means, but this only holds under independence. Otherwise, it will not hold. You will have to go to the specific video on the properties of the mean to see a proof of this and some examples. Now let's go back for a moment to the temperature data set and look at another limitation of the mean, which is that it is so succinct, it gives us like such a short description of each of the random variables that it can obviously miss important differences between them. So these were the mean temperatures of these 134 weather stations in the US. It turns out that these 3 weather stations have exactly the same mean, but when you look at their distribution of temperatures, they're very different. It immediately jumps out that there's much more variation in this station in Missouri than in this station in California. So it is often very useful to be able to capture such variations, and that's why we define the variance. But before that, actually I got a little bit ahead of ours. No, actually, in order to define something that captures the average deviation, which we're going to call the variance, which is the average squared deviation, we will need to somehow quantify the magnitude of the deviation. How do we do this? I got a little bit ahead of myself, but how do we compute the magnitude of a real number? We take the absolute value. What is the absolute value? We square the number, and then we take a square root. How do we compute the magnitude of, or Euclidean length of, a vector x? We sum the squares of the entries. Why do we sum the squares of the entries? So that there's no cancellations between negative and positive entries. And after summing them all up, we take a square root. Well, for a random variable, we're going to do something very, very similar. We're going to take a square so that positive values and negative values don't cancel each other. Then we're going to average. We're going to take the mean of the square. And if we want to quantify deviation, we will take the square root of that. So if we want to apply this to quantify variations in a random variable, what we're going to do is we're going to say, okay, we're interested in the random variable minus its mean. Let's take a square so that there's no cancellations between positive and negative variations. And then let's take the mean, okay? This is called the variance of a random variable, and it captures its fluctuations. If you apply linearity of expectation, you get a very nice expression in terms of the mean of the square of the random variable minus the square of the mean. And that's what we usually use when we're computing variances in practice. As I just mentioned, the square root of the variance is a reasonable measure of the average deviation of a quantity. What do we do when we try to estimate the variance from data? We take each of the data points, we subtract the sample mean, because that's the best estimate that we have for the mean. We take a square, we sum over all the data points, and then we divide by the number of data points. We don't really divide by n, we divide by n minus 1. This is not too important. It's just so that the estimator is unbiased. We will talk about this stuff later on, but this really does not make much of a difference in practice. The sample standard deviation is obtained by just taking the square root of the sample variance. Okay, so these these quantities that had the same mean in our data have very, very different standard deviations. The standard deviation in Missouri is more than 3 times larger than the standard deviation in California. So we get another number that actually tells us a lot of information about the random variables. So just like the mean told us immediately that it's hotter here, the variance tells us immediately that there's very large variation in temperature within the United States, like inside the continent, whereas in the coasts, the variations of temperatures are much less. The Northeast coast, which is unfortunately where I live, more variation. But it is what it is. All right, so now that we have defined the mean of a random variable and also the variance, let's consider how we could estimate the mean of, or how could we define the mean of a quantity when we know the value of a related quantity. Okay, we're going to call that the conditional mean function, and essentially what we're going to do is we're going to estimate the mean of the quantity of interest, which is b, but we're going to use the conditional distribution of b given the quantity that we know. So immediately, this conditional mean is going to depend on the value of that quantity. That's why we express it like this, where it's a function. Okay, so this says that this is the mean of the random variable b given the random variable a, when the random variable a is fixed to have this value. So when that value changes, the mean is going to change. In the case of continuous random variables, we essentially use the same definition, except that, as usual, we replace the probability mass function by the probability density function and the sum by an integral. Let's take a look at here. I think it's important to actually show you a couple of examples so that we fix ideas. These are 2 random variables a and b that can take 3 values each. What if we know that a, for example, is equal to 1? What is the mean of b? Well, these are the relevant values of the joint probability mass function of the 2 random variables. We can compute the conditional PMF from this slice of the joint PMF by renormalizing it so that it sums up to 1. This is the result. And now we just compute the conditional mean using that conditional PMF, okay, where we sum over all the possible values of b multiplied by the conditional PMF when a is equal to 1. In this case, that is equal to 15 divided by 7. And as I said, if we condition on a equal to 1, then we obtain a certain value, 15 divided by 7. If we condition on a equal to 2, we have a different conditional PMF and hence a different conditional mean. And if we condition on a equals 3, again a different conditional PMF, different conditional mean. So that's what I meant by the conditional mean function being a function of the value of a. That function is only well defined when this conditional PMF is well defined. Otherwise we cannot define it. What about continuous random variables? So let's use this usual example that we use when we're talking about continuous random variables, where there's an otter that is, swimming in this lake, and we represent the position of the otter as a random variable that has constant density inside the lake and 0 outside. So the PDF is equal to 2 because the area of the triangular lake is equal to 1/2. All right, so now what if we know that? I always like drawing this picture. I'm here. I see that the otter is somewhere here, but I don't know exactly where. What is the mean, given that the mean of this horizontal coordinate given that information, where I need to use the conditional PDF, which is equal to 1 over 1 minus a. Okay, it's basically constant from here to here. So the conditional mean is going to essentially be the midpoint. And you can see that the midpoint is going to change depending on the value of a, roughly like that. This is exactly what we're going to get. The conditional mean function is equal to the integral with respect to this conditional PDF. When you take that integral, it's exactly this midpoint that I was talking about. We can plot this function. I don't know why I haven't plotted this function. I wanted to, you know what happened? It's under there, okay? But you can imagine it, okay? It's going to be equal to 1 minus a divided by 2. and I am not going to re-record the video, but it's buried under that slide. Hopefully, I mean, here I've drawn it too, right? Like this is the value of the mean function. It's defined from 0 to 0.5 because those are the values that we get for values of a that are between 0 and 1, where the conditional mean function is well defined. Again, you have like a more detailed description of this in the video on the conditional mean function. How do we estimate the sample conditional mean? And this is very important, as we will see later on, for regression. Well, you essentially do like for the mean, except that you only use the relevant values. So if you're interested in the mean of a quantity b, which is, corresponds to this second entry in these pairs, and you want to condition on the first entry, the random variable that represents the first entry being equal to a certain value a, you're going to basically look for what pairs that value is equal to a, and you're going to average the second entry of those pairs. Okay, this is what this bag of values is, all the pairs for which the first entry is equal to a, and then you compute the average of the second entry. This is kind of more complicated than actually just looking at an example. Imagine that we have these movie ratings where people rated 2 movies. So for example, 3 people gave a rating of 2 to Independence Day and 1 to Mission Impossible. And now imagine that we want the average of Independence Day when Mission Impossible is equal to 3. What are we going to do? Well, we average these particular values of Independence Day. And here you can see what happens if we do that for each of the possible values of Mission Impossible. What if you have a continuous random variable? These are temperatures at Kentucky, Versailles, Kentucky, and Corvallis, Oregon, over a year. So each point corresponds to the temperature in Versailles and the temperature in Corvallis. We can represent this as samples from a 2-dimensional random vector that has this joint PDF. Now, how do we compute the conditional mean? You could actually just apply the formula to this conditional PDF that you have estimated from the data, or more pragmatically, you can just say, I want the conditional mean at 10. Then I'm going to take a slice around 10. You cannot just take a line exactly at 10 because you're not going to observe any pairs for which the temperature at Corvallis was exactly 10 because these are continuous quantities. And you're going to basically average the corresponding values of Versailles. If you do this for this data, you get this conditional mean function, where here it's a little bit noisy because we don't have a lot of samples that we're averaging over. Okay. It turns out, and this is actually a very tricky concept, that if you take the conditional mean function and you plug in the variable that you're conditioning on, you get a random variable. Okay, so here we had a deterministic function of a. If we plug in a, we get a random variable. And we can take the mean of that random variable, and it turns out that that mean is the mean of the quantity that we're interested in. This is kind of weird the first time you see it. It's called iterated expectation because first you take a conditional mean with respect to a certain variable, for example, a, and then you take another mean with respect to a, and that gives you the mean of the quantity that you're interested in. This is super useful when you have access to the conditional distribution of b given a. This allows you to compute the individual conditional mean values and then aggregate them to get the mean that you might actually be interested in, which is the mean of b. If I explain this in detail, then the video would go on for another 20 minutes, and I don't want that. So you can go to the video on iterated expectation to get a lot more information about this. This can also be applied to functions of the 2 random variables. Again, same idea. First, we compute the conditional mean given a, and then we compute the mean of that, I don't know why I put an arrow there, and then we compute the mean with respect to a, and that gives us the mean of the quantity that we're interested in. All right, so I said a moment ago that the conditional mean is actually very useful for regression. The problem of regression is trying to estimate a quantity from another quantity. So if we have the rating for Mission Impossible here, what should be our rating for Independence Day? Here, if we know the temperature in Corvallis, what should be our estimate for the temperature in Versailles, Kentucky? In general, we want to find a function h that maps the values of the known quantity to estimates for the unknown quantity. Here, the unknown quantity is a random variable b, and the known quantity is represented by a random variable a, where we observe that it's equal to this value. An important question is, how should we evaluate this estimator? A reasonable general purpose metric to evaluate estimators is the mean squared error, which basically just takes the difference between what we want to estimate and our estimate. We take the square, as we said before, so that there's no cancellations, and then we average. So just so that you visualize what we're doing, we're basically taking the difference between the quantity we're interested in and our estimate for all possible values, but we're weighting more those that have higher density, or if the values are discrete, higher probability, which makes a lot of sense. So in order to try to reason what could be a good estimate of a quantity given another one, let's imagine that you just want to estimate a quantity represented by a random variable and you know nothing. You only know the PDF of the random variable or the PMF of the random variable. So then you can just produce a constant estimate. Well, the best constant estimate in terms of mean squared error, okay, so this is a constant, this is a mean squared error. If you minimize this with respect to the constant, the best estimate is actually the mean of the random variable. So in that sense, also the mean is kind of a typical value of a random variable because it's the best possible estimate in terms of mean squared error. So what would you do if you know that another quantity that is related has a certain value? Now, how should you estimate B? Well, it sounds very reasonable to just use the conditional mean of B given A. And in fact, that's the minimum mean squared error estimator. You cannot do better than the conditional mean in terms of mean squared error metric. For some applications, you might care about other metrics. So in the case of the movie ratings, the best you can do is you take the average. So if you know that the rating for Mission Impossible is 2, your estimate is going to be the average of the corresponding values for Independence Day, in this case 3, and so on and so forth. For the temperature in Corvallis and Versailles, if you know the temperature in Corvallis is 20, you're going to use the mean temperatures when it's 20 in Corvallis, which is around like maybe 24 or 25 in Versailles, Kentucky. Okay, and that's the best you can do in terms of mean squared error. All right, so we have arrived at the final topic, which is causal inference. Here we want to estimate a causal effect of a certain treatment or a certain intervention from data. As an example, imagine that I decide to write the title of this video in all caps. And now I want to know if that is going to cause the video to have more views. In this case, the treatment would be this decision to put the title in all caps or not. And what I'm interested in, the data and also the observed variable that I'm going to monitor, is the number of views of the videos. So in order to frame the problem of whether the all caps title actually causes the video to get more views, we define these things called potential outcomes. The potential outcome for treatment 0 tells us how many views videos would get if we never put any title in all caps. Conversely, the potential outcome for treatment equal to 1, which we write like this, tells us what views videos would get if we put all videos with all caps titles. What we actually observe is the outcome for treatment 0 when we put a video that does not have an all caps title, and then we observe the outcome for treatment 1 when we put a title that is all caps. What do we really want in order to estimate the average causal effect of the treatment of putting the title in all caps? We want the mean of the potential outcome associated to treatment 1 minus the mean of the potential outcome associated to no treatment. Can we just compute this from the data? We cannot, because we're not observing these potential outcomes directly. I cannot just put all titles in all caps and at the same time put all titles in not all caps. This is impossible. Instead, I have a situation where I have to choose. So for some videos, I decide to not put the title in all caps, then the observed outcome here is 102 views, corresponds to the potential outcome for no treatment. I have no idea what would have happened with the treatment. So this is a counterfactual. Same for this second video. It's not in all caps. I know what happened if I don't put it in all caps. I'm just observing it. No idea what would happen if I put it in all caps. Conversely, if I decide to put a title in all caps, I see the views for, I do not see what would have happened if there was no treatment. I do see what would happen if there's treatment. All right, and this happens for each single data point. So now, again, these missing points are counterfactuals because they're counter to reality. They're what would have happened if I had done something else. Well, we don't know. The key question here is whether I can just average these guys and subtract the average of these guys to determine the causal effect of changing the title. Is that a reasonable estimate for the average treatment effect, which is the difference between the means when there is treatment and when there is no treatment? And the answer is that you cannot always assume that this is a reasonable estimate. It can actually be a severely distorted estimate. To see why, let's take a look at what this conditional mean looks like. We're conditioning on the treatment being equal to 1. This is actually equal to the conditional mean of the potential outcome associated to treatment, given that the treatment is equal to 1, which sounds like good news because we want the mean of that potential outcome. The problem is that this mean is going to be computed with the distribution of the potential outcome given treatment equal to 1. And if we're treating different videos than the ones that we're not treating, so for example, I'm putting in all caps my most popular videos or my oldest videos that tend to have more views because there's more time maybe for students to watch them, then that's going to completely distort the average. What we would really want is the average with respect to the true distribution of the potential outcome, and that can only be achieved if the potential outcome and T are independent. The first time you see it, you would be like, how it could be the treatment, how could the views be independent from the treatment? You have to realize that these are the views if you put all the videos in all caps. So what this really means is that videos that are being chosen for the treatment group are not systematically different to the videos that are not chosen for the treatment group. This can be achieved by just randomizing, choosing what videos to put in all caps by flipping a coin. In that case, this is a perfect estimate of the mean of the potential outcome associated to treatment. Same thing under that independence assumption for the videos that were not put in all caps. And in that case, we can estimate the average treatment effect as the difference of the conditional mean functions for treatment 1 and treatment 0. I actually did this for my YouTube videos this semester. Randomly, I put 19 in all caps and 26 in no all caps. Okay, this was a random decision taken by flipping a random coin flip in Google. And what I found out is that essentially the average treatment effect is 0. The means are really, really close. I can derive like a conclusion about causal effect from this because I have randomized the treatment. Otherwise, I would not be able to take this conclusion because of the possible confounding factors. Again, randomization immediately, automatically neutralizes all possible confounding factors because it enforces independence between the potential outcomes and the treatment. This is the box plot of the views of the videos with all caps and the videos with not all caps. In fact, actually the median for the proper case, non-all caps titles is slightly higher. So we can really conclude that all caps really makes no difference, at least for my type of videos. And that's all I got. For some reason, I didn't create a slide about what we have learned, but basically we have learned that in data science, we use averaging all over the place. It's super useful. We defined the mean of a random variable. Then we defined the variance of a random variable, which is also obtained via averaging. In this case, we average the squared differences. Then we talked about the conditional mean, which is the average given another quantity, and we saw that it's optimal for regression in terms of mean squared error. And finally, we saw that when we're trying to quantify causal effects by averaging, we have to be very careful in case there's confounding factors, and that randomization helps us to neutralize them. Thank you very much.